In the last video, I promised that I would step through code, not only my own code, which is not very big and doesn't get into the guts of the calculations, but now I'm going to go through and step into the Qiskit code, which is IBM's code used for quantum chemistry and also for quantum computing. Okay, let me explain the screen first. Here's an area where we can look at variables and different internals about the program as it's proceeding. And down here is the terminal window, which will show us the output from the computer. Now I'm going to start with a super simple main script, and you'll notice it does the main menu, and then it does the experiment runner. So what we'll be in almost the whole time is inside this experiment runner. So I'm going to go up here to run and start debugging, and it starts running, and there we go. There's the menu. We're going to calculate molecular energy. The molecule is helium, and that's chosen because that's just about the simplest situation we can perform that still requires an approximation of those Gaussians that I talked about in the previous video. The simplest basis is this 3 Gaussian version of it, and this STO stands for the Slater type orbitals, which is what the 3 Gaussians is trying to approximate. Mapper is Jordan Wigner. I'm not going to spend much time on that. And the solver is as close to an exact solver as we can get. So, accepting all of those inputs, I'm going to type a 0, and that 0 will tell it to accept that and start running the program. Here we are into experiment runner, and the very first operation is build a molecule. That sounds good. We've got the molecule and the basis. So what we're loading into it is helium and STO3G. Now I'm going to execute the program up to the next breakpoint. Build molecule function. Let's see what the molecule looks like. Well, what is this? The mol equals GTO, Gaussian type orbitals. And the Gaussian type orbital molecule is going to be described in a file. We'll notice that we load up this mol object, which this just prepares the object. It doesn't load anything into it. Here we're loading the atoms. The atoms came from the molecule data file. The molecule basis, well, we already know that that's the basis, STO3G. The charge and the spin came from the molecule data information. Now we're ready to actually build the molecule. Let's see what happens next. Here we're picking up the file name, STO3G, no big surprise there. Now we're loading the file name, and we're actually going to look in a basis folder that has some different values in it. And where would this file be? Well, if we go over to this area here and look at the actual file name, let's see if we can find it. Here's the basis, and if we look at this file, here's all the numbers. These numbers are already calculated, and this explains the references. These are the Gaussian coefficients that come up with the shape of the Gaussian approximations. It created a formatted version of the information about the molecule and the basis. Now that we've built the molecule, we're going to calculate some of the electronic structure, which the electronic structure involves some integrals. So we'll see what happens to those integrals. Here we're setting up this thing called PY self-contained field driver, and we're loading the information that we just put into those files. Here we are talking about our first one electron integral overlap, which is the first step in evaluating the integrals. Now we're doing another one electron integral, kinetic energy, nuclear attraction, and an integral between the two electrons, helium atom. Now, if we get into more complicated molecules, then we have several of these two electron integrals to solve. One integral for every pair of electrons that we can come up with. Now we're into the polynomial tensor. And after we complete that driver, we're down here to returning the result. Let's see what kind of results we have. There's the geometry. That was dealing with the integrals. Now we're into the second quantization coefficients. We're getting deeper into the molecular model. In this case, it's just an atom with two electrons, helium, dealing with that polynomial tensor. And we're back out to this part of the equation. Time to map some qubits. So let's see what we're doing with the qubits. Here we're using the Jordan-Wigner mapper. Back inside this fermionic mapper class, which that's a new one. So that's another piece of the pie inside the Qiskit environment. We were inside Jordan-Wigner mapper. Now we're inside the qubit mapper. More mapping. And we've completed the mapping phase. Let's see what happens after the mapping phase. Now we're going to get ready to solve for the energy. If we look in the watch window, energy equals none. Then after we perform this function called the exact solver, after we report the energy, then we notice that it's this negative 2.8 Hartrees. That was rather quick, but it's probably good that it was quick because I didn't have a lot to say about each of those different elements, but I did fulfill my promise of getting into the Qiskit code. And I noticed myself that one of the things I left out that was very important was the exact solver of the energy. I just plopped it out there, gave the results, and didn't say anything about how it got there. So we did a good job, I think, of the Gaussian approximations that came from the file. So there was actually no calculations needed at all there. So what can we draw from all this? Well, the stuff that we didn't get into was, how does the computer solve integrals? I don't know what to say about that, because I don't know how that does that. What about the mapping, the qubit mapping? Well, there's a lot more to expand on that. So maybe what's better is to have separate videos after this used as an overview will work to pique your curiosity into the detailed versions of how the software's actually doing its job.